Hello, I am Professor Ghosh of the Department of Physics at IIT Bombay. I am going to be giving 20-hour lectures on a subject which is an evolving subject known as quantum information and computing. Let me take a bit of a time in explaining to you what is this subject about. It is an emerging subject in many IITs and ICERs, and many students of both engineering and physics take it as an elective at the moment. The course requires familiarity with subjects such as linear algebra and operators and matrices. Basically, you need some familiarity with these subjects and an exposure to the principles of quantum mechanics. This exposure does not mean that you should have been familiar with solutions of Schrodinger equation, but it requires more a familiarity at the level of philosophy of quantum mechanics, which is normally given to all students of science and engineering in first and second year of the university or engineering colleges. So, let me begin by telling you what is this subject and who are going to be benefiting from it. Firstly, let us look at what is classical computing all about. If you know, a computer has basically two components. One is known as a hardware, that is the basic electronics and circuitry on which the computation actually proceeds, and the second one is the software or the algorithms and programs based on which people provide logic to such a system. Now, what has been found is that in the modern electronics, which depends upon integrated circuit, there is a law which has been governing how speed has been increasing very fast. This law is known as the Moore's law, which essentially says the population of the transistors in an integrated circuit has been essentially doubling every 18 months or 2 years. Now, at that rate, the sizes of these electronic components become smaller and smaller, and their spacings between them naturally becomes much smaller. However, there is a limit to which you can make them small. The ultimate limit is when they reach atomic dimensions. Of course, even transistors and diodes and things like that, as you know, they work on the principles of quantum mechanics, but however, the classical computing has always been based on classical logic. By that I mean the following. Supposing you take an NAND gate. Now, according to the classical digital logic, if the input of the NAND gate is 1 and 1, then the result has to be 0. Now, this is where the quantum mechanics differs from the classical thing. Now, in a quantum computer, the input and naturally the output can exist in a simultaneous superposition of many states, and this provides an inherent parallelism to such computation processes. Now, this results in a very interesting aspect, that is known as a quantum entanglement. Now, entanglement of states is not being able to write a quantum state as product of two states is something which is very peculiar to quantum mechanics. This both parallelism and entanglement, it provides a tool for doing computation with speeding up which has never been thought possible before. And for instance, development of quantum computing is still in a nascent stage and only the laboratory prototypes are available, but as we are aware, the technology leaps. So, when the futuristic quantum computers come and arrive commercially, we must be prepared for it. So, there are two specific large scale algorithms that I would like to mention. One is a database search. A database of n items typically requires in classical computing of the order of n searches. There is an algorithm known as Grover's search algorithm. Now, this search algorithm speeds up this quadratically, namely instead of the order of searches being n, it becomes square root of n. That is a substantial speeding up. But the more interesting one is the way one can factorize a large composite number which is known to be product of two prime numbers. As we know that in classical computing, this is a non-polynomial time algorithm. Now, there is an algorithm due to Shor which has made it possible to factorize such large numbers in polynomial time. Now, that has tremendous application in future communication protocols, because today's algorithms which govern, for example, even transactions that we do with banks and all that, are based on what is known as the RSA algorithm, which is based on the principle. While it is very easy to find product of two numbers, it is not possible to find the factors of large composite numbers in polynomial time. However, Shor's algorithm has been shown to be possible to do so in a polynomial time. Having done that, we will introduce what are known as the elements of quantum cryptographic protocol, that is secret communication, secured communication for sending information from one end to another. This course will start with components of a quantum computer, go through the essential linear algebra, and we will also introduce postulates of quantum mechanics which are necessary enabling quantum computation, and finally we will prepare ourselves for writing down. There will be actually no programming techniques done here, but the algorithms for some of the major problems that can be handled with quantum computation will be done. With that in mind, I believe the people who can benefit from such a course would be primarily the faculty of physics, electrical engineering, and the course is nowadays being given in IITs and ICERs as elective courses, which are being taken by students of physics and mathematics, as by many engineering disciplines such as electrical engineering, computer science, etc. So, I hope you will be able to enjoy this course, which is essentially a futuristic course with the principles of quantum mechanics and computer science wedded together. Thank you.